So first of all, we have to talk about what is radioactive decay and how does it occur. Some isotopes are unstable by nature because they have large size, and because of that large size or the too many number of neutrons inside the nucleus, we have an imbalance of forces within the nucleus, and that imbalance can cause and emit radiation and decay of the atom itself or the isotope itself. So the isotope can decay to become a more stable isotope, and in that process radiation happens and then will form some release of energy in form of particles or waves. So the nucleus will release either particles like this particle here or some waves or rays to be more stable. And the process of emitting those particles, this is what we call radiation, and in specific we call it radioactive decay. That decay then will explain that the nucleus will try to become more stable by releasing some energy within its core, and this will reduce the overall energy within the nucleus, making it more stable, as we said. And that radioactive process or radioactive decay is very random, and we don't have control over it. The rate of decay, however, is very steady and very stable, but is not affected by the surrounding conditions of the nucleus. Therefore, the emissions of any isotope can be described as spontaneous and have random direction. There are three types of radioactive decay that we will talk about. So we have the alpha decay or alpha radiation, and beta decay, and also the gamma ray radiation. So let's talk about the alpha radiation first, where we get a release of two proton particles and two neutron particles from the isotope in the form of the alpha particle release. In other words, we can say that the alpha particle is equivalent to a helium atom when we look at the structure of its nucleus. So helium is 4-2, and then when we talk about the alpha notation or the alpha particle, we know that they release two protons and two neutrons, so it's 4-2 as well. Now let's discuss the beta radiation. So beta radiation is a negative charge release or negative particle release in the form of electron, or similar to the electron nucleus, not the atom itself, but beta has a negative charge like the electron, and its mass is very negligible because electrons, as we say, they are very less in their mass, and they are negligible mass. They have a negligible mass. And the notation for the particle is 0-1, so 0, -1, and also 0 protons and neutrons, and -1 electron. The gamma rays radiation, they release a larger amount of waves or energy in the form of rays and waves from their nucleus. The gamma radiation, since it does not release any particles, it's very neutral, does not have mass or charge. Thus we can say that it does not carry mass or charge, and it does not need to be indicated with any notation, 0 and 0. Now let's talk about the radioactive decay and how does it happen. We said that any unstable isotope, in this case we can say that this parent isotope, which is the original unstable isotope, has large size or large number of neutrons in its nucleus. It will try to become more stable by being a radioactive isotope, where it will release some, let's call it radiation, and that radiation then will release some daughter isotope, which is more stable. So this daughter isotope will be more stable, has a lesser size and lesser number of neutrons. And in that release, we will expect to have some alpha, beta, and gamma radiations. Or one of these three. So the radioactive summary or the radioactive decay summary, we know that we can have alpha particles and beta particles or gamma rays. This is the structure of the alpha particles, 2 protons plus 2 neutrons, and the beta is similar to an electron structure, and the gamma doesn't have any particles, it's an electromagnetic wave. The charge, this is +2, the alpha radiation, beta is -1, and then in terms of range where they can travel through air particles, alpha can travel a few centimeters in air, and then beta can travel between 10 to 15 cm. Gamma rays cannot be stopped by air. They can penetrate through air, and then they can only be stopped using lead. And then beta particles can be stopped using aluminum sheet, and then alpha particles can be stopped using a paper sheet. In terms of ionization, the particles that have largest size, which is the alpha particles, have the highest ionization, and then beta and then gamma rays have the lowest ionization. Okay, now let's move on and talk about the half-life. So the half-life is the activity of a sample, and when it's reduced to exactly 50% of the initial amount, we call that the half-life, and we can determine it using a half-life graph where we look at the starting activity of a radioactive material, and then when that initial amount is reduced by 50%, we say that this is the exact half-life of that radioactive isotope or radioactive material. For us to measure the radioactive count, we need to use a radioactive counter like the Geiger-Moller counter or GM counter, which is present on this left image right here. The half-life graph will represent to you the percentage or the amount of radioactive material that we have at time equals 0, and then as time increases, we expect a decrease in the amount of the radioactive particle, and then we can say that this amount is reducing in an exponential function or decreasing in an exponential function. As the time decreases, the number of particles inside the isotope will decrease as well due to the decay. And different isotopes will have different half-life cycle or half-life duration, where some of them can take up to a fraction of a second, and then other isotopes will take billions of years to decay.